Hey everyone, welcome back to Calculus 1. This will be lecture 5 of the course, and in this section we're going to finish up the broader section on limits, kind of an introduction to limits. In this section specifically, we're going to be discussing infinite limits, so kind of a final little piece that we need to plug into the puzzle so that things will make sense as we start to use limits to construct other key infrastructure in calculus. So let's go ahead and jump into it. We'll call this section 1.5, infinite limits. And so as per usual, let's start with an example, right? And so here's the function f of x equals 3 over x minus 2. Now I've gone ahead and plotted the function off to the side here, and you can see that the function if we approach 2 from the right-hand side, the function tends to infinity. And if we approach 2 from the left-hand side, the function tends towards negative infinity. And so another way to say this is that the function increases without bound as x approaches 2 from the right, and decreases without bound as x approaches 2 from the left. And we can denote this behavior using this notation, right? The familiar limit notation. And so what this says is that the limit as x approaches 2 from the left of 3 over x minus 2 is equal to negative infinity. Now earlier we saw that under our previous definition of limits, we can't have a limit at infinity because infinity is not a real number. So what we're doing now is we're augmenting that definition with this additional piece so that we can use this kind of common language and we can say that the limit of a function is plus or minus infinity. Right, so in this case, the function goes to positive infinity from the right, negative infinity from the left, and so we would write it like this. Right, it would have a left-hand limit and a right-hand limit, and they're not the same, as you can see. But these are called infinite limits, right? And so this is different than a regular limit. And that difference is spelled out clearly or cleanly, nicely, concisely in the definition, right? So this is an additional definition that is needed because this is not a regular limit. Regular limits are real numbers. These are not regular limits, they are infinite limits. These are limits at infinity. Okay, these are limits of infinity, rather. So let's read through the definition. What does it say? Let f be a function that is defined at every real number in some open interval containing c. C is the limit point. Okay, so you got an open interval around some limit point c. F is defined everywhere in that interval except possibly at c itself. And this is very important because this is the infinite, this is the vertical line where the graph goes infinite, right? And so what do we mean when we say that the limit as x approaches c of f of x is infinity? What does that mean in terms of like the epsilon delta sort of level of understanding? Well, in the case of an infinite limit, what it means is that for each m greater than 0, the idea here is an m as large as you like, 2 billion, 150 trillion, whatever, however big you like, arbitrarily large. For any arbitrarily large m, there's going to exist a delta greater than 0 such that if I want to prove that the function is larger than that m, i.e. that it truly does go to infinity, I can do so by just getting within delta of my limit point. Right, so this is real similar, a similar kind of machination to the epsilon delta proof that we discussed earlier. But here, the idea of being within epsilon of a particular point is replaced with being greater than m, right? So the function is larger than m rather than being within an epsilon, right? And so the idea is that this m can be as big as you like. However large I want to make it, I can always find a delta if this limit is true, right? So just getting closer and closer means I'm further and further up on the y-axis. So the idea, for example, here would be, hey, if I want to show that this truly does go to infinity, one thing I could do is give you an arbitrarily large number and make you prove that the function value is greater than that when I'm very, very close to 2, right? And so that's the idea behind infinite limits. And it's very similar in the case of the limit being negative infinity, and we, instead of saying m is greater than 0 and m can be arbitrarily large, we say that n is less than 0 and n can be arbitrarily small, right? Meaning small, meaning more negative. It's a large in absolute value, but negative, very, very far out on the negative number line, right? And so similar, if we look up here, if I want to prove that this goes to negative infinity, what I can do is I can say, well, I can pick an arbitrarily large negative number and show that whenever I'm within a very close, whenever I'm very, very close to 2 from the left-hand side, I'm way, way down here below this number, right? So that's the idea behind the definition for infinite limits, right? Similar concept to the epsilon delta proofs in the normal limit definition, but adjusted because this is a different thing, right? Okay, very good. Let's go ahead and move into some examples. So let's consider this example. The function f of x equals 1 over x minus 1. Okay, so you look at this and you immediately recognize that we've got an issue with the domain of this function at 1, right? Namely, if I try to plug a 1 into this function, I get 1 over 0, which is a no-no, right? And so we might conjecture, we might initially think there is a vertical asymptote here. Actually, we would be correct in thinking that. So the question is, what is the limit of this function as I approach it, as I approach 1? Okay, so we know that the function has a vertical asymptote at x equals 1. Now, how do I know if the function goes to positive infinity or to negative infinity? Maybe it does, maybe both sides go to negative infinity, both sides go to positive infinity. How do I know? How do I test this? How do I figure this out? Well, to see where the function goes, as they say, as x approaches 1, i.e., does it go to positive infinity or does it go to negative infinity? What I can do is I can just test some values close to 1, right? Test a value very close to 1 on the right-hand side. So I could test like 1.01, for example. If I want to know what happens to the function as it approaches 1 from the other side, I could test, 0.995, for example. Right? And if the value that I get when I plug those in is positive, that's going to indicate that generally the function is headed in the positive direction. If I plug those values in and I get a negative number, that's going to imply the reverse. Right? But let's just keep it simple here. Just know that you can test values that are very, very close to your limit point, or just so long as you're on either side and you're capturing the true behavior of the function. But let's go ahead and just plug in some easier numbers. Let's plug in x equals 0. And so if I plug in x equals 0, I get 1 over 0 minus 1, and so negative 1. And so just looking at the function after I plot it, I can see that indeed this function does go to negative infinity as I approach 1 from the left-hand side. Similarly, I can plug in x equals 2. And when I do that, I see that the function is 1 over 2 minus 1, so the value of the function is 1. And so that's going to tell me that the function approaches positive infinity as x approaches 1 from the right-hand side. Okay? And so that's a simple way to test whether the function goes to infinity on both sides, positive and negative and positive, whatever. Right? So you can just test values near your limit point. Very good. So we've used the term vertical asymptote a number of times already, right? I think I might have been using the term already in lecture 1. Now, sometimes in algebra, this term will come up and you will encounter it, vertical asymptotes, slant asymptotes, horizontal asymptotes. But in a context of calculus, we can define this now using limits, right? So the definition that we'll run with for vertical asymptote is that if the function approaches plus or minus infinity as x approaches some number c, then the line x equals c, right, namely the vertical line in the plane at x equals c, is a vertical asymptote of the graph of f. Okay, so basically we're saying a vertical asymptote is going to exist if the function tends towards plus or minus infinity as we get closer and closer to the value c. Okay, and so we can kind of use limits now to identify vertical asymptotes, and let's take a look at an example of that. So let's determine all the vertical asymptotes of the function f of x equals x squared plus 2x minus 8 over x squared minus 4. Okay, so I've got a ratio of two polynomials here. And when you have the ratio of two polynomials, what you might be inclined to do is do some factoring. And indeed, you can factor these nicely. So the top factors into x plus 4 times x minus 2. Right, so I've got these two factors. And the bottom we see is x squared minus 4, which factors into x plus 2 and x minus 2. Right, and so I've color-coded these, and you can see that the x minus 2's cancel out. But we're stuck still with this x plus 2 in the denominator. Okay, and so ultimately, though, this function looks an awful lot like x plus 4 over x plus 2. Now, the only difference is that this guy here is not defined at x equals 2 because technically you still have this factor in the bottom. But everywhere else, these two functions are going to be equal. Okay, so let's take a look at this thing. What does it look like? Well, here's a drawing of this function, kind of plotted in the interesting sections, right? And so you see here's 2, right? And then negative 2 is over here. I didn't label it on the plot, but that's negative 2, right? And so look at what happens here. So as we saw when we factored this, right, the x minus 2 cancels, right? And that's going to correspond, that discontinuity is going to correspond to this guy, isn't it? Right? So it turns out that as we approach positive 2 from the left and the right, the function doesn't deviate from this sort of normal shape that it's laying out, right? And that's because you have an x minus 2 in the numerator, and these two are basically undoing each other. But when we do get to the critical value of 2, the function does have a hole, right? And so when you see things like this in the denominator, it's either going to be a hole or it's going to be an asymptote. Now, if it's a hole, it'll cancel with something in the numerator, or it'll be undone by something in the numerator. But if it's an asymptote, then you're stuck with it, which in this case, you can see is the case with negative 2. So negative 2 is the asymptote. So we get asymptotic behavior here, and we get a hole here. Okay. So this example shows us that f is undefined at x equals 2 and has a vertical asymptote at x equals negative 2. Right? And so this x equals 2 issue, this is an example of a removable discontinuity, and the x equals negative 2 is an example of a non-removable discontinuity. And so you can kind of see the logic in naming them this way, right? You can just plug something else in, but these things kind of get removed by this cancellation here. Very good. So we can use the idea of the limit to help us understand when we have vertical asymptotes, when we just have holes. Okay, let's take a look at another example. What about this function? So I've got f of x equals x squared minus 3x over x minus 1. We can see just by looking at this that we're going to have a vertical asymptote at x equals 1. Right? Now the question is, does this thing go to infinity, plus or minus? Is it the same from both sides? So what we could do is we could just apply that testing approach. Right? So let's test on either side. So we could plug in x equals 2, and that would kind of simulate approaching 1 from the right-hand side, right? So we plug in x equals 2. When we do that, we get 2 squared minus 3 times 2 over 2 minus 1, and we see that the value is negative 2. And further, we can see that as we approach 1, as we approach 1 from the right, the value of the function decreases. Right? I've plotted the function. And a similar test from the left would show that the function increases, right? Now, the one thing about this function is you do need to be careful that you're getting close enough, right, to the limit point, in this case, 1. So, for example, if I were to test like -1, then I would get a negative value, and that might trick me into thinking that, oh, the function actually goes to negative infinity. So it's always a good idea to test as close. I mean, if you have access to a calculator, you can easily calculate these things. Test as close as you can to the limit point, reasonably, like, within a reason, so that you are sure that you're capturing the right behavior, right? If it's going negative, you want to make sure that you're capturing it. If it's going positive, you want to make sure you capture that. An alternative, in this day and age, everybody has graphing calculators if you're taking calculus. So plug the function in, get a look at it. That'll obviously tell you what the limits are going to look like if they're infinite. Okay, very good. Right, so in this case, again, just to underscore that notation, we would say that the limit as x approaches 1 from the left of this function is positive infinity, and the limit as x approaches 1 from the right of this function is negative infinity. Okay, very good. Okay, so this is great. So we've talked about finite limits in previous lectures, and now we've talked about infinite limits. Now, sometimes these two worlds collide in the case of certain functions. And so we have a theorem that tells us how to deal with functions that have maybe a term that's infinite and a term that's finite, or maybe a product that has multiple different pieces, and the two pieces are multiplied together, and one of them's infinite, one of them's finite. So what happens with the limit in those instances? Okay, and so what this says is, let C and L be real numbers, and let F and G be functions. Okay, F has an infinite limit as x approaches C, and G has a finite limit as x approaches C. Okay, so I've got these two functions. One of them has an infinite limit, and the other has a finite limit. So what happens if I add these two functions? What happens to the limit? What happens if I multiply or divide these functions? What happens to the limit? And so here it's nicely itemized for us. So the limit as x approaches C of f plus or minus g, right? Think about this. This f is going to infinity. G is going to a finite number like 5. What is infinity plus or minus 5? Well, obviously it's infinity, right? And so the sum or difference is infinite, right? Again, if this is infinite and this is 5, what's infinity minus 5? Infinity. All right. And so similarly for products, if f of x goes to infinity and g of x goes to a finite number, then the product of that is going to have an infinite limit also. Now, whether or not the limit is positive or negative really kind of depends on g, doesn't it? All right, remember, f just goes to infinity. G is going to go to some finite number. Now, if that finite number happens to be positive, then the limit will be positive infinity. If that finite number happens to be negative, then the limit will be negative infinity. Okay, and so hopefully very intuitive, right? This is infinity times 5. This is infinity times negative 5. Well, I'm on the negative. I'm in the negative direction, but just infinitely far down in that direction. Okay, so these three are straightforward. Now, this one here, the fourth item here, g of x over f of x. So what happens if I have, what's the limit as x approaches c of a function with a finite limit and over a function with an infinite limit? Well, just think about division. If I take a number, a finite number, and I divide it by something infinite or something very, very, very large, we can see that that's going to produce something close to 0, right? And so the limit as x approaches c of g over f is 0. Now, in a later lecture, later on in the course, we will discuss what happens and how to deal with this situation when f and g are flipped, when the infinite limit is on top and the finite limit is on the bottom. But we're not going to talk about it yet, right? We're going to start with this one, and that's all we need for now. Later, we'll get into this other case, or what happens if they're both infinite, what happens if they're both zero. We'll get into that stuff in a later lecture. So for now, we just have these four kind of straightforward, hopefully straightforward scenarios. Let's do a quick example just to make that a little more concrete. Consider the limit as x approaches 1 of sine of x plus 1 over x minus 1, right? So I've got kind of two terms in this sum. The sine function, the limit there is going to be, finite. It's going to be less than infinity, we'll say. And the limit of this one as x approaches 1, well, we know this has got a vertical asymptote. We talked about this example earlier. So this is going to go to infinity. All right, so if we think about the individual terms of this function, it's clear that sine is going to be finite, and 1 over x minus 1 will not be finite, right? So I've got finite basically plus infinite, and so that means the limit will be infinite. And I've actually gone ahead and drawn this one out. I try to draw all of them, just it helps with intuition. But you can see as we approach 1 from the left-hand side, the function heads off to positive infinity. As we approach from the right-hand side, it heads off to negative infinity. Right? So one way to write that would be to say that the limit as x approaches 1 of sine of x plus 1 over x minus 1 is just plus or minus infinity, right? And if it's important, you can specify by having two statements from left or right, right? So that is a nice example of using this theorem and specifically this piece. Okay, very good, very good. That'll do it for this lecture. In the next lecture and up next in general, we're going to get into derivatives, differentiation. And so this is one of the highlights of Calc 1. It's one of the key pieces of innovation for mathematics in general that we get from calculus. So derivatives and differentiation up next. All right. With that, thanks everybody for sticking around, for keeping up with the lectures, and we will talk to you all next time. Take care.